Well, welcome. Today is rainy Monday, January the 25th, and we're just here at Spain Park doing a little bit of chemistry. Getting fired up about it, that we're finishing up the unit on bonding. Okay, so we talked about ionic bonding. What's the key word in ionic bonding? With electrons. They form ions, but how do you form the ions? What do you do with electrons? Transfer the electrons. Metals lose, nonmetals gain, metals become positive, nonmetals become negative, and they attract to one another. What's the key phrase in metallic bonding?
Shared.
That's covalent.
No, that's the C of electrons.
The C of free-floating valence electrons. And since we have those charged particles that can flow, it gives metals that unique characteristics, being able to conduct electricity as a solid or a liquid. Makes them malleable and ductile, okay? And then in covalent bonding, that's sharing. And that's what we've been spending the majority of this unit on, is covalent bonding. Now, when things bond covalently, there's two ways in which they can combine. They can either be a covalent network, where it's this network of atoms covalently bonded. Okay, remember there were 5 things that were covalent network, and that's how you're gonna know it's just one of those 5. What are the 5? 5 things to know if it's gonna be covalent network.
Silicon.
Silicon.
SiC.
Silicon carbide, which is used as an abrasive.
SiO2.
SiO2, which is also known as sand.
CO.
Carbon, just C, in 2 different forms. What are the 2 forms of pure carbon?
Graphite and diamond.
Graphite and diamonds. And I had the models up here, and other teachers borrowing the models. Okay, where diamonds were that 3-dimensional carbon bonded to 4 other carbons, grew in 3 dimensions, the hardest natural substance. All of those 5, and the way you know, again, you have to just know those 5. That's how you know it's covalent network, because they're all nonmetals, and so we just have to know that. But when they bond, they have the covalent, and they don't form molecules, they form these big crystals of atoms covalently bonded to one another. And we saw on the IMF worksheet that the covalent bonds are way stronger than those IMFs. So things that are bonded strongly with covalent bonds takes a lot of energy, a high melting and boiling points to break apart. So diamonds, you don't think about a diamond melting very easily. You have to heat it up very, 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 very hot in order to get a diamond and or graphite to melt or react, okay? Because they're strongly bonded. All other covalent compounds form unique individual molecules. Those molecules are what are held together then by those weak intermolecular forces that we were talking about in detail on Friday, Thursday? When did we do the IMF worksheet? And we went over, I went over
Thursday.
on Thursday, and then we talked about it on Friday. Okay? Those IMFs are super important. That's what's holding covalent substances, but they're weak, which means that covalent molecular substances tend to be liquids or gases at room temperature. Now, we want to talk about the properties of covalent substances. And one of the main properties that's important to us is the concept of like dissolving like. Do you have any idea what that means? Solubility. Like dissolves like. Any guesses? That means that polar solvents dissolve polar or even ionic solutes. And you know, solute is the thing you're dissolving, solvent's what you're dissolving it into, right? So if you put sugar into water, sugar's the solute, water's the solvent. You've all learned those terms before. So the opposite of this is true, is nonpolar solvents dissolve. If it's like dissolves like, nonpolar is going to dissolve nonpolar. Okay? Now, the most common example of this is the most common example of this. Oh, I lost my whole train of thought. It's paints. You have two different types of paints. When you go to Home Depot or you go to Sherwin-Williams, you want to buy paint. You can either buy latex, which is a water-based paint, or you can buy an acrylic, an oil-based paint. Okay? Now, water-based paints are nice and convenient, and that's what most people use nowadays, because after you use it, you can use water to clean it up, because it's based on water, so everything's dissolved in water, so water will dissolve all of the paints and everything in it, and you can just clean your brushes and do everything. You clean off your hands, you know, you can clean up easily because it's water-based. Oil-based paint though, you try to mix water with it, it's just gonna get all gumpy and nasty, so you have to use mineral spirits or turpentine, some oil-based, some non-polar solvent in order to be able to rinse it off. Now, an example of this, okay, I don't know, let's make sure I'm still on it here. Have y'all ever heard of the term polymer? Have you ever heard of a polymer? Do you have any idea what it is? Okay, have you, a monomer, what do you think a monomer is? One of them. Okay, so the most common monomer looks like this. It's called ethene. This is a monomer. Okay, mer just simply means the building block, the starting material. So it just takes one mer. Now, it's got this single bond, it's got this double bond with a sigma and a pi bond. Well, if you mix another one with this, okay, and you have, sometimes they need a catalyst, sometimes you have to heat it up, they have their own way to do this chemical reaction, but when they link this, they can break the double bond, the pi bond. And that makes each carbon now have another bond. So they can link together, and you end up making this, and it can actually continue on just forever and ever. You can just keep linking them together. You keep breaking this each carbon, so then this carbon can form another bond here, and then you can put another one and another one and another one, and you end up getting a polymer, a polymer. Many mers all linked together. I mean, like hundreds of thousands. Super long chains. Okay? So this is called ethene or ethylene. This is going to be called polyethylene. Now, if you've ever looked at the recycle symbols on the bottom, you know, you have the little triangle with the arrows. It looks like that, and then they put a number on the inside. Number 2, they'll say HDPE. High density polyethylene. Okay? That's just going to be this, and high density is just going to be how many carbons are in the chain, and sometimes they can add things that kind of link them together like spaghetti noodles. You can kind of get them all tangled up, and that makes it stronger. So it's the difference between a milk carton versus the plastic bag that you get at Walmart, you know, to put your food in. And so all the different types of plastics. They also have low density polyethylene, and you have all different types of plastics, but all of these are hydrocarbons. Now, have you ever heard of a PVC pipe? Does anybody know what PVC stands for? Okay, it's polyvinyl chloride. All they do is substitute in on the monomer, they substitute in the chlorine. It's for one hydrogen. So this is ethylene chloride, okay? And actually the old school name of this is called vinyl. So we had
Vinyl seats.
like vinyl seats in a car and stuff. It's made out of this same polyethylene. It's vinyl. Okay? So, but when you mix them together, what's going to happen is every other carbon, every other one is going to be a chlorine. That just adds strength to it. And so it's called polyvinyl chloride. which we shortcut PBC, because nobody knows what polyvinyl chloride really is, okay? But it's still gonna be a symmetrical molecule, but this adds hardness to the molecule, makes the pipes a lot firmer, okay? Gives them unique characteristics. I say all of that to lead us to styrofoam. Styrofoam, you start with this, but instead of having a chlorine here, we have a carbon in a ring. A hydrogen, a hydrogen, a hydrogen, hydrogen. Now that's a real pain to draw, so we can shortcut that and just kind of draw it like this, and that represents all the double bonds, and you assume there's hydrogens everywhere. So these two things are the same. This is just a chemist shortcut. But the whole point is that you have this, and then you have this. This compound right here is called styrene. So when you link them together, you get polystyrene. So the only thing different between it is that you have a benzene ring here rather than a chlorine or a hydrogen. The whole point is that these are all hydrocarbons, they're all nonpolar. So polyethylene is nonpolar, you know, the vinyl is nonpolar. All of those are nonpolar substances, okay? Now, have you ever been to like a food court where they give you not just the styrofoam tray, but they give you actually a hard tray, you know, just a normal tray to get your food on? You guys know what I'm talking about, okay? But before they came out with all the styrofoam. That tray is actually polystyrene. It's the same exact stuff as styrofoam. It just, they don't blow air through it to make it porous. It's just much more dense. And so this styrofoam cup and a cafeteria tray are made out of the exact same thing. They just blow bubbles, they blow air through this and make it have little air gaps all throughout this to make it a good insulator. Okay, just a little tidbit. So we know, go turn it a little bit this way. We know that styrofoam then is a non-polar substance. So if I take polar water and I put it into my cup, it's awesome. I mean, it's perfect. It's because it's got the trapped air, it makes it a good insulator. It doesn't conduct electricity, conduct heat well, okay? You can put, and this is the amazing thing, this is a miracle of science. You put a hot thing in, it stays hot. You put a cold thing in, it stays cold. How does it know? How does it know? It's a miracle, okay? The reality is it just doesn't allow heat in or out, and so it stays the same temperature no matter what you put in because it's insulated. But notice it's doing great. But let's just say that you get some paint on your hands or you have fingernail polish and you want to, you know, get it off, and you know, I've seen commercials where the ladies just kind of hold their fingers into the, you know, especially if you get like a gel on your fingers, you got to kind of hold it in there to kind of get it to dissolve to get the new gel, right? Well, let's just say you want to do that at home, and you get some acetone fingernail polish remover, and you put it, you say, oh, I just got a styrofoam cup, let me just put it in a styrofoam cup. So you just pour a little bit in there and you just get ready to go and put your fingers in there. But lo and behold, just very quickly, you see we have a problem. Very quickly, we see we have a problem. Very quickly, this is a heavy duty styrofoam cup. A little bit more. I've never had this problem before. No, starting to see it. Okay, so what happened is the whole bottom kind of all gave way. Okay, the whole cup is just kind of coming apart because it's slowly dissolving in the acetone. Okay, and so it's like dissolves like. This is nonpolar. Acetone is a hydrocarbon. It's nonpolar, and so the two together, it's going to dissolve the other thing. Okay. So we want to be real careful on what we're mixing, because if you want to get something to be removed, you want to have something that's very similar. Now, just a little tidbit here. Have any of y'all ever heard of the napalm, like a napalm bomb? All napalm is styrofoam dissolved in gasoline.
And then it sticks to you or whatever.
Do what?
Then it like stick to them.
Yeah, then it makes it, instead of the gasoline being a liquid, it makes it real thick and a gel. And so you throw it against something that sticks to it and makes it burn way better. Now, do not attempt this at home, okay? It is dangerous, but that's all napalm is just a jellified gasoline mixture of styrofoam where they just make it super saturated and make it thick. But like dissolves like. So we talked about oil-based paint and water-based. Dry cleaning is the same thing. Rather than using water as your solvent, dry cleaning does not use a dry powder to clean your clothes. It just uses a non-polar solvent. The actual solvent is tetrachloroethylene. It's going to be the same exact thing. And I don't know what it is about this. Fancy word. Tetra, meaning four. Chloro, the chlorines, four chlorines, ethylene. And we talked about this being ethylene, just when it's hydrogen. So we're substituting the four hydrogens with chlorines. Now these all have lone pair around them. But notice it's a perfectly symmetrical molecule, so it's nonpolar. They used to use carbon tetrachloride, which was just one carbon with four chlorines around it, but they found that this was a carcinogen. When I looked this one up, it still says it's thought to be a carcinogen, but apparently there must not be enough medical evidence because all dry cleaners pretty much use this. Okay, so it's a liquid. They're going to wash your clothes in this liquid, and you can smell when you get your clothes back from the dry cleaners. You can kind of smell that chemical coming off of it. It's got a unique odor to it. So if you have a whole bunch in your closet, dry clothes that are dry cleaned, you need to just make sure you leave the door open, air it out, so you don't get super high concentrations of this, because it is thought to not be super healthy for you. Okay, so girls especially, some of your fancier dresses and things all have to be dry cleaned. Guys, most of our jeans and pants and shirts, they just all don't wash together. Okay, but the reason is because sometimes water might have a negative effect on the substance. Okay, so we want to have something with dry cleaner, and so it's just like dissolves like. It's polar dissolves polar, non-polar dissolves non-polar. So any stain remover, if you want to get mustard out of something, you want to find something that's got a similar structure to mustard to make it dissolve. Now the problem is that it can't be similar to the dye in your clothes or whatever you're trying to get it out of, because otherwise it'll just leave that white spot or bleach it out. So stain removers all try to figure out, okay, so what is common stain? What will dissolve it but won't dissolve the other thing? All right, lastly, along the exact same lines, I take some cyclohexane. It's a hydrocarbon, okay? Cyclohexane. And I put it just into a test tube, okay? And I take some iodine. Let me just kind of give you the cyclohexane. It's going to be very similar to benzene, it's all single bonds. And then there's going to be two hydrogens coming off of each one looking like this. These are all hydrogens. Now you don't have to know that. I'm just showing you that this is a hydrocarbon. Hydrocarbons are nonpolar. Iodine looks like this. Okay? Iodine looks like this. So what do you expect this to be, polar or nonpolar? Nonpolar. So, if I take some iodine, okay, now notice, see how nasty this is? Iodine is a unique substance in that it sublimes. This is a solid inside of here, okay? But it's all sublime, so the vapor gets, it just goes straight from a solid to a gas. The vapor tends to escape out, even though this is tight, it's not a perfect seal. So those vapors can slowly work their way out and do all kinds of damage to this bottle. So if I take a scupula, and just get just a itty bitty little bit. I want a little bit more than that, but I put that in there. Let's go just a tad more. God, it does not want to stay on this. There we go. So now I take this, and when iodine dissolves, or if I heated this up and you saw the vapor, it's going to be purple. It's pure iodine is purple. And so when it dissolves as this nice purple color. So it's like, dissolves like non-polar, completely soluble. But if I just take some water, if I just take some water and try to do the same thing, just put some iodine into this water, what do we expect to happen? So now I shake it up, and basically it's not dissolving, it's just sitting on the bottom. Okay? Now, if I mix these two things together, come out, most of it. Okay? So now, you never want to just stick your finger over the top. So I'm just going to get a paper towel. And I shake it, baby. So now we look here, and it's going to quickly separate because the water and the oil don't mix. But the iodine that was sitting down at the bottom, it reacts and made this even darker because I put even more iodine now, so it dissolved in there. So I get my two very distinct layers of the water on the bottom and the oil on top. This is what we call an emulsion. This is not in your notes, so you need to write this down. An emulsion, a mixture of two immiscible liquids. Okay? They will quickly separate. Okay, so it's an unstable emulsion. It's going to quickly separate. Now, immiscible means insoluble. So two insoluble liquids, but when two liquids are insoluble, they use the term immiscible. They came up with a new word, I don't know why. Okay, but immiscible simply means they're not soluble in one another. So the water and the cyclohexane are immiscible, they don't combine. Okay? But we can add what's called an emulsifying agent, something that links them together. So we have normal Italian salad dressing. There you have Italian salad dressing, you had to shake it up, get the oil and the vinegar to mix, and then real fast you got to pour it onto your salad. Okay? Because they're going to quickly separate again. But if you have creamy Italian, they've added egg whites to that, and so it won't separate. Mayonnaise is oil and vinegar, but they add egg whites. It's an emulsifying agent. It allows the two things to stay linked together. okay? So if I take just a little bit of alcohol, ethanol. Ethanol looks like this. This is the alcohol in most alcoholic beverages, okay? It's sometimes used as rubbing alcohol as well. Just you either get isopropyl or ethanol as the rubbing alcohol you buy at CVS or Walgreens, okay? But notice that we have this whole part right here is a hydrocarbon. It's nonpolar. This part over here, though, with the oxygen, remember phone call, this part is polar. So we'd say the molecule as a whole is polar because it's got phone call, it's asymmetrical. So if you're taking the test and you want to say, is this polar or not polar, we'd say it's polar. But really, just this end of it is polar. The rest of it is kind of nonpolar. And so this part likes nonpolar solvents. This part likes polar solvents. So this part will stick to the water. This part will stick to the oil and kind of link them together. Now notice that the iodine is not soluble in the water at all. But if I put some alcohol in here, I put some alcohol in, now I shake it up. Now you can see that some of the iodine is able to dissolve in the water. The alcohol is very miscible. Immiscible, just take the IM off. Miscible, what do you think it means? Soluble. Very soluble. Alcohol and water are very soluble. So the alcohol and water are mixing. But the alcohol then, because it has this nonpolar part, it's allowing some of the iodine to stick with it. So the brown is going to be your iodine. Now this kind of cool color, purple and gold, go Tigers, okay? And so this is a good LSU demo right here, but we see it now is that it's allowing some of that iodine to dissolve into the water. And the more I shake it up, the more that's going to dissolve. And I don't know if you've ever heard of a tincture of iodine or monkey blood. They use this, they used to use this a lot to clean before they did surgery. Okay, it was that yellow, now they use beta iodine, betadine, and so they use something other than alcohol, because alcohol will burn if you had any kind of cut. And so they try to make it to where it doesn't burn. But it's just an emulsifying agent. It links the two things together. The most important emulsifying agent that I can think of is soap. Okay? Soap. Soap has a long non-polar hydrocarbon end, but it's got a polar end on the very end. Let me see, I should look this up ahead of time. Is that bad?
Mm-hmm.
That doesn't sound good.
It's got some hot on it. So, this is your drop of oil. If you go and you take a shower, you take a bath, and you don't use any soap, especially if you don't use any shampoo on your hair or anything, it's still going to be oily when you get out, okay? The water and oil just don't mix. So we need to have something when we go and take a shower or try and wash our hands or do anything, we have to have something that's going to link the two together. So soaps are the stearate ion. That's the most common, okay? Each of the black is a carbon, so we have this,
And it all depends upon what they make the soap from. Back in the day, soap was made from lard, which is pig fat, or tallow, which is sheep or cow fat. So when they would slaughter the cows and the sheep, they would take the fat and you send it to the soap company. And you treat that fat and it makes soap. So the fat goes from here. Now I remember that back in the 70s there was a commercial about Tone with cocoa butter made from coconut oil. Different things, have different characteristics. So this hydrocarbon chain can vary as far as what it is, but the whole point is it's a hydrocarbon and it's going to be nonpolar. So what does hydrophobic mean?
Doesn't like hydrogen.
Not hydrogen. Doesn't like
Sorry,
water. Okay, the phobic means fear. It's a fear of water. It doesn't like water. Whereas this is the hydrophilic end, meaning
It likes water.
loves water. Phileo is love, okay? The love of water. And so this end, because those red ones are oxygens, that makes this very polar over here on this end. So this end, you can see the non-polar end goes and attacks the oil droplet. But then the water can come in and attach to the polar end and link the two together. And so you get a water here, you get a water here, you get a water all the way around it. And that pulls the oil. And now it doesn't make the oil soluble in the water, but it links the two together to where then it can wash down the drain. It's called an emulsifying agent. It links two immiscible liquids together and keeps them from separating. That's how all soaps and detergents work. Now the only difference between a soap and a detergent is that soaps are made from natural substances like the lard and the tallow. A detergent is made from something man-made, like an oil. A lot of times a soybean oil is what they use now. You can actually make soap from Crisco shortening. Just treat it with sodium hydroxide, which is commercially known as lye, and you can get soap, okay? The whole point of soap is that it's got a long nonpolar end that attracts to the oil, the nonpolar, and then it's got a polar end which attracts to the water and it links the two together. That's how all soaps and detergents. So when you're washing your clothes have little tiny pores in it. And the water will form that film. Have y'all ever heard the term surface tension? The little bugs that float across the water. Why do we put our hands out when you dive in? It moves the water apart, right? Because it hurts when you hit that top layer of the water. I was really going to skip over this, but I can't help myself. So if you have a beaker of water, or a lake, or a pond, or a swimming pool, and you have the water right here, okay? You have a water molecule here that's being attracted in every direction by other water molecules that are completely surrounding it. Does that make sense? So it's pulled evenly in all directions by the hydrogen bonds, by the dipole-dipole, by the London forces, but it's completely surrounded by other water molecules that then they're being pulled equally in all directions, and so it's all just kind of moving around. But on the surface up here, the water molecules on the surface are only being pulled this way, this way, this way, and this way. There's nothing pulling them up. So there's an unbalanced force pulling them in and down, which is why we get that meniscus when you pour water into a graduated cylinder, because it's pulling down, but yet then it's attracted a little bit to the sides of the glass. But it wants to try and get as close as possible because it's an unbalanced force. So you have like a skin across the surface of the water due to that unbalanced force. Which is why when you dive in without your hands, it hurts your head. As soon as you get through the top layer, it doesn't hurt to go through the water. It's just this top layer has that surface. They say that after so many feet up, jumping into water has the same effect on your body as landing on concrete. And so, especially if you land flat rather than, feet first. So if you go cliff diving or whatever and you do a belly flop, you can be serious, it can kill you. Whereas if you go in feet first, then you can go down. So surface tension. So when you wash your clothes, these little pores get that layer of water across it that has that surface tension that doesn't let the dirt out. It traps the dirt. So what you have to do then is you have to break down this, and you have to have what's called a surfactant, which basically just breaks down surface tension. It gets in between the molecules and doesn't let them attract as strong. Have y'all ever heard of Surf detergent? It was like Tide, it was an old, but it was named Surf. I don't think they make it anymore, they changed it, but it was called Surf because it was a surfactant that was just short and kind of a cool name that, you know, it's Surf. But it was just like Tide, just like any other detergents, okay? And all they do is they break down, they do the exact same thing as the soap, they just break down the surface tension and allow that dirt to be able to attach to the water and escape through the pores. So, it's all about like dissolves like. Polar dissolves polar, non-polar dissolves non-polar. We can link them together with an emulsifying agent. A substance that's got a polar end and a non-polar end. The most common one being soap, okay? But egg whites are used a lot in Italian salad dressing and mayonnaise. There's emulsifying agents used in many, many things to keep things that don't want to mix together.
Don't they like put egg whites in people's hair or something? Like you put like egg whites in it and like it's...
Probably, because it'll help draw out stuff, or, you know, I don't know, but, you know, look at this hair, I mean, I don't, not much you can do with this one. Gray hair is really nasty too, because it just does whatever it wants to do. It's not, you know, when my hair was normal, I could comb it and it would stay and whatever. Now it just kind of does whatever it wants to do. All right, so how do dry cleaners work?
They use a liquid that is not water, so it doesn't destroy it.
What type of liquid, polar or non-polar?
Non-polar.
Non-polar, because water's polar, so they use something opposite of that, okay? Does that make sense? Now, the last page of the notes, all about liquids, I mentioned surface tension or whatever, but we're not gonna really do much on that last page dealing with liquids. We'll touch on that when we get into solutions. We'll talk about the properties of liquids and boiling and that. So you really now have all the information you need. And so I posted a study guide today. You can use the last 10 minutes or so to start working on that study guide. Tomorrow when you're at home, you can work on the study guide, and you have all day Wednesday to work on the study guide. It's gonna be due Wednesday night at midnight. And then Thursday, I'm not gonna post the key, but I'm gonna go over it. So y'all will be beneficial that you'll be here in class. I'll go over it, but I'll also video it and post the video so those of you at home can see, you know, go over it and have all the correct answers, and then test on Friday. And you guys won't be here, but you have to take the test during class time. All right, Sam, you'll be here, but so it's really just you two are gonna need to take it during class time. And if all possible, I think I have an answer sheet on that. If you can print the answer sheet out, do all your answers on the answer sheet, and then rescan it, that'd be great. Now, you don't have to print the whole test out, just the answer sheet. I can't remember what the test has an answer sheet or if it's a write-on test. But if you don't print it out, just try to format the answers in a logical way that I can easily grade. Okay? Yes, ma'am.
We do the study guide like on the computer instead of writing it out.
No, I'll let you write it out. Because if I let you do it on the computer, then one person does it and everyone kind of shares it with them. I want to see your handwriting.
Are we not gonna create 16 space guide?
Oh, yeah, I got them right here. Okay, you can turn them.